Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online NPTEL structural geology course, and in this week we are learning folds and folding, and in this particular lecture we will learn superposed deformation of folds. So this week is a little long for you because we have 4 lectures of quite long hours, but this is how it is. Fold is one of the spectacular features as we have discussed in previously. So we decided to spend quite a lot of time in learning folds and different features, but good news, this is the last lecture on folds, and as I said, today we will be learning superposed deformation of folds, and we are in lecture number 23. So the things we learn in this lecture, the first one is the basics of superposition of folds. Then we will try to figure out the different morphologies and the classification of superposed folds. And finally, we will see what are the different outcrop patterns of the superposed folds. So we will take one after another with a lot of descriptions, illustrations, and also some field examples. So let's first understand that what is superposition of fold, or get the basic idea what it is. Now, if you remember in the previous lectures, we have seen some folds where the fold axis is curved, or the axial plane is not very much a straight plane. Now, to give you an example of this, for example, so you can consider that you had this initial straight layer, something like that, and then it got folded to form a shape like this. So this is an antiform. It is an upright fold, and so on. Okay. Now, what we see here, the fold axis is this one, which is straight. The axial plane, if you can consider, is also straight. Now, in this setting, we see that there is only one deformation that has happened. So the deformation came from this side to make this fold. But we have seen folds which are non-cylindrical. For example, we have seen a shape of a fold something like this. Where the fold axis is not straight but curved, and interestingly the axial plane is straight, and this we have identified as a non-cylindrical fold. So to form this, it is very much clear to us, if we understand the stress lecture, that to form this kind of curves in a straight layer, we need a deformation, layer parallel shortening, layer parallel compression. So after that, after this structure has formed, this particular one, you must have to have another deformation almost perpendicular to the previous one, the compression, that could curve this fold axis which was initially straight. And this is the basic concept of superposition. So you have formed a structure, and then you modify the structure with a second or third or fourth deformation which may be similar to the previous one or may be different to the previous one, and this is the basic concept. So to produce these complex structures, so you can infer the fact that in an orogenic belt there might be more than one system of folds which will interfere with one another. We will learn about more on these kind of structures and features throughout this lecture. Now here is an example just to orient you. As you can see here, that this is an outcrop. This is a photograph from John Ramsay, and you see, if I just first try to understand the fold closer, then I see certainly we have a closer like this. So it is closing in this side, and then we have series of closures which is closing upward forming antiforms, and then series of closures this way forming synforms, and this happened in a single layer. Now if I try to draw the axial traces, and if I consider that this is a profile plane of this fold, profile section of this fold, then if I consider this is the folded layer, then certainly the axial trace would be something like that. And interestingly, the axial trace is not a straight line. So therefore, the axial trace got curved. And how did it get curved? It got curved because you have another fold which I see, the axial trace of which are like this, and in this case the axial trace are very much straight. So one the axial trace which is curved, one the axial trace which is straight. Our common intuition says, at least looking at it, that the blue one must have formed initially and then it got refolded with this green one. So this is how we look at and interpret things. Now we will learn these things in more detail with different other kinds of structures and features, but this is something, an example of the superposition of folding. Now how it can happen? Now fold interference may take place either synchronously, that means you can have shortening along the layers in all directions, so not a particularly oriented direction, but all sigma 1, sigma 2 and sigma 3 if you consider on a plane. So sigma 1 and sigma 2 you can consider that these two stresses, these two principal axes of stresses are equal, or it can happen successively, that means one after another, which was the example I cited at the very beginning, that you have compression along this direction, so you made a fold, then you have compression along this direction, then you curve the fold axis. So this is how it occurs. Now this successiveness, that one after another deformation, can happen in three different ways. So it can happen when a single continuous deformation is going on, but the orientation of the stress axis are continuously changing. That can happen in an orogenic belt. Now it can also happen in the course of a single orogeny, which within which there could be some sort of superposition of separate phases of deformations with different orientation of the stress and at the same time incremental strain axis. And you can have superposition of deformation that can belong to different or separate orogenies. So there could be many possibilities, and we'll look at each of them, but first we'll see the first kind of features where it can deform synchronously. That means you don't need two stages of deformation or one after another or successive deformations. So in one single event you can produce superposition of fold. Whatever be the case, you have your initial structure and then you get your final structure by superposition. So the second one is known as refolded folds. So here is an example of interfering patterns in a single deformation. So this is these two, what you see, an experiment. The first one, it was a circular canister or something like that you can consider, and the stress axis, it got compressed from all directions equally. And then it was a modeling clay, and then you can see here that these are your fold axes and they are not necessarily oriented equally, and also from the shades you can figure out that fold axes are not straight. In this case, the second example, you see the buckling is happening, you can understand by the shapes of these shadows and things like that. So these are fold axes and you can clearly visualize that these are not straight, they are some sort of getting branched and so on, and in this case the deformation was directed mostly due to shortening in two directions. So this is what can happen in a single deformation, but this kind of features we see in the field but not very common. So we will not focus in this particular type of deformations a lot, but we will figure out that how we can see these things in different stages of deformation. Now, first generation of folds generally is refolded by second generation and by all subsequent generations. So, we have a first generation fold, then it can get refolded by second generation, it can get refolded by third generation, and so on. Now, you can imagine the fact that the features, particularly the fold axis and axial plane, which are developing in the first generation of folds, can get modified in the second generation of fold. At the same time, the second generation of fold can also produce a different fold axis and a different axial planes, and so on. So, it is important in the field we identify which one is what and also correlate them with the deformation. So, generally we study it mostly based on overprinting relationships, that is, how was your first fold axis, then how it got modified by the second deformation, and what was the orientation of the fold axis of the second deformation, and so on, and also we consider this with the axial planes. So, one is the direction, that is the plane, and then we correlate them with the deformation. So, we have three terminologies. One is surfaces that we are producing successively, then we have fold axis which we are producing successively, and they correspond to the deformation. So, surfaces are defined as S. If I denote as S0, where 0 is on the index position, so S0 or S0 means that there was no deformation. So, this was generally considered as sedimentary surfaces or bedding plan. Then you generate your first axial surface, second axial surface, third axial surface, and so on, and these are assigned as S1, S2, S3, and so on. Similarly, F0 is hardly used because that means there is no fold, but then you produce successively fold axes like hinge lines or fold axes on first, second, and later generations, and then you refer them as F1, F2, and F3, and so on. And these S1, S2, S3, F1, F2, F3 should be correlated with the deformation. So, D0 means no deformation, and then deformation sequences you can go with D1, D2, and D3. So, in a way S1 should have F1 and that should be correlated with D1, S2 should modify S1 and produce F2, and that deformation should be correlated with D2, and so on. So, this is how we learn in the field, how we will identify these structures in the field and also interpret them successively. Now, as we talked about that the classification of fold superposition is based on mostly the geometry of the axial surfaces and the hinge lines or the fold axis of the first generation fold. And in that case we can have four possibilities, 2 for the axial surfaces and 2 for the hinge lines. So, axial surfaces could be either plane or non-plane, and hinge lines could be either cylindrical or non-cylindrical. So, combination of these 4 would give you the classification of superposition of folds, which is in the next slide. So, first classification is type 0, which is known as plane cylindrical. That means the fold axis is straight, therefore it is cylindrical, and axial plane is also not curved, it is straight. So, therefore it is plane cylindrical. Type 1 fold superposition is plane non-cylindrical. Axial plane is straight, fold axis is curved. Type 3 is non-plane non-cylindrical. Both axial planes and fold axis are not straight, they are curved. And in type 3 what is remaining, it is non-plane cylindrical. Axial planes are curved, but fold axis is very much straight. What is written within the parenthesis here, that redundant superposition or dome basin pattern, dome crescent mushroom pattern or hook pattern, these are the structures or superposition outcrop features that you see in the field. We will learn about it later after we classify or we see them through some geometric considerations, and then we will go how we form this dome basin, crescent, mushroom and hook patterns. Now, the majority of these complex folds are mostly produced by superposition of buckling deformation. So, you do not get it by bending and so on. So, it happens mostly due to the buckling fold mechanism, which essentially is a very complex process, and people still work on it because it is not very well understood and it is very hot topic in structural geology research community. So, in any event, the distinction among the 4 categories of these superpositions can be made entirely on the basis of their morphology and without considering their mechanisms and so on, but people generally try to correlate with the mechanisms. But in the field, you mostly identify by their mutual relationship and so on. So, we will learn about it soon. Let us focus on type 0 fold superposition. So, initially cylindrical planar, and after deformation it is also cylindrical and planar. That is, the initial fold morphology does not change after the deformation, it may get tightened only. So, what you see here, this is your initial fold. You can see the fold axis is straight here, and in the refolded fold that simply tightened this fold, the fold axis are also straight here. So, it is cylindrical before and after deformation. If I consider the axial planes, I just draw one here. This is the axial plane of this fold. It was straight plane, and here it is also very much straight. So, therefore, this is plane cylindrical superposition, and this is type 0 fold superposition. Now, here is a movie, short movie. You can see how does it work. So, you see here it just the fold gets tightened and tightened and tightened, but it can happen episodically. That means the deformation can stop and then it can start again, but without changing the orientation of the principal axis of stresses or the direction of layer parallel compression. Now, let us have a look what is type 1 superposition. As we have defined, so initially cylindrical planar, and after deformation it turns to non-cylindrical and planar. So, here again if I consider the fold axis in this initial fold is very much straight, and here we will assign this as F1. So, that means these are the folds of the first generation, fold axis of the first generation, and axial planes, if we draw only one, is like this, and this we assign as S1 because this is something which is being developed on a surface which you can consider as S0. So, this is your S0, that is your form surface or initial bedding plane and so on. Now, after the deformation, if we try to trace the fold axis F1, we see that F1 now is very much curved, then it went inside, then it is coming back again here, it went on the other side and so on. So, F1 is clearly folded. So, this is your F1, this is also your F1 and so on. Now, who is folding the F1 or who is refolding the F1 is something, a different fold which is appearing here that you can figure out from this. So, this is your F2. The S0 is again here the form surface, which is this brownish layer. Now, if I try to consider what happened with the S1, we can clearly see that S1 is still very much straight, though it deformed in this direction, but the fold, the axial plane is still very much straight. So, this was your S1, and that did not become curved due to the second stage of deformation. What is also important, that if I try to draw the S2, then S2 probably would appear if I just this section, actually this section you are looking at, this section is parallel to S2. However, if I try to draw, the S2 would appear something like that. So I have F1, I have F2, I have S1 and S2. In both cases, we see that S1 and S2, they remain planar. So it is planar deformation, but F1 and F2 both are curved, therefore the fold is not cylindrical, and therefore it is non-cylindrical planar superposition or type 1 fold superposition. We have again a movie for this. Let's have a look. And now the superposition started. You see how F1 is getting folded by F2. Let's consider the type 2 fold superposition. So initially, as we have defined, a cylindrical planar fold would turn to a non-cylindrical and non-planar fold. So again, this is your initial fold. I again define all these features. This is your F1 and this is your S1, where this is S0 as the form surface, and that happened in D1. In this case, I just draw it with the same color. The stress came from the layer parallel shortening happened in this direction. Now if you deform it from this side, after that you may have a shape like this. Let us see what happened with the F1 after the deformation. You can clearly see that F1 is now running like this. So F1 is not straight anymore, therefore fold axis, initial fold axis F1 is non-cylindrical. What happened with the S1, which was this one? We can also see, I draw it here, the S1 is also curved. As it is going here, because it is intersecting the plane in a curvy way. So S2 is also, sorry, this is S1. So S1 is also curved. So F1 is non-cylindrical, we have established, and S1 is not planar anymore. So this is non-planar. So a non-cylindrical, non-planar fold we have developed due to fold superposition, and this is type 2 fold superposition. What happens with F2 in this image? And you can see that this fold axis, this red line here, is getting folded by, of course, F2. So F2 is coming this way. So this is another fold. This is another fold axis of F2. And if this is F2, then you can guess that what would be your S2. Now I am not drawing it, it is up to you, you figure it out how this S2 would look like in this image. We will see this later in many cases. So this is type 2 fold superposition, where we develop non-cylindrical, non-planar refolded folds. And finally we have this movie. So you see how does it develop. Is this clear to you? I believe. Now we will look at type 3 fold superposition, where, as we have defined, initially cylindrical planar, and after deformation it becomes cylindrical and non-planar, and this is also known as coaxial folding, and we will see why. So again we do the same process as we have been doing with the other superpositions. So this is your F1, this is your S1, and again the form surface is S0. Now what is happening with the F1 after the deformation? We see that F1 is straight, it did not get curved or it did not change its orientation. But S1, interestingly, if we try to look at this plane, it is now extremely curved and it is going like this, isn't it? So if I try to do the actual trace, it would be something like that. So S1 here is very much curved. Now who is curving the S1? Of course, it is happening due to the deformation. So where is the F2? F2 is sitting somewhere here. So all these secondary curvatures that you see here, here and so on, these are your F2. Now you clearly see the orientation of F1 and F2 are parallel to each other, and because they are parallel to each other, these are known as coaxial folding, where the fold axes are oriented very similarly. Now where is the S2 here? You can figure out from these folds that S2 is lying something like this, and in this case S2 is very much straight. So this is how we develop the type 3 fold superposition, which is known as coaxial folding or cylindrical non-planar folds. And here is the movie again for this type 3 fold superposition. Brilliant. So this is how you develop type 3 superposition of folds. Now we have a very clear understanding of how to define or how to classify this type 0, type 1, type 2 and type 3 fold superposition as given by Professor Ramsey. There are some other classifications. Professor Ghosh has came up with another classification which is based on modes of superposed deformation. We are not going to learn this, but you certainly can refer the book of Professor Ghosh that I have recommended at the very beginning of this lecture, and this is also very interesting to look at. Now let us talk about the outcrop patterns of fold superposition. But before we jump into the actual topic, let us understand what do we mean by outcrop patterns. Now we have seen all these kinds of folds. Actually we have seen many different geometries. So in all these 3 folds that we see here in this slide, these are all antiforms, and this is an upright fold. The fold axis in all cases are very much straight and so on. So what do we mean by outcrop patterns? That we just have seen the geometries, but they can appear on the surface in different ways, because they not necessarily will appear the way we see them or we draw them. What I mean by this, that this fold, after they are formed, they can break or we can see them in any sections, and these are their appearance on the outcrop scale. What do I mean by that? If I make a horizontal section like this here, then the fold will appear. I have to use a different color because I don't have this color here. So if I try to trace them on the horizontal surface, on this green surface, and if I plot this green surface here, then the 2 limbs would appear on this surface, something like that. In a very similar way, if I try to do with the next one, the plunging fold, and if I take a section along this, you see that it has to cut on this side, so it probably would look like on the surface something like that. And if I do the same for the third one, I am sorry, it would be opposite. This should be thinner, and this would be thicker. So these are the outcrop patterns of this fold, these three folds what we have drawn here. Now can we draw the axial trace? The answer is yes. So in this case the axial trace would be something like that. Again it is here like this, and here these are the axial planar cleavages that would form successively like this, like this, like this, and so on. So if I try to draw the traces, they will appear here as the traces of these axial planes on this surface, or axial planar cleavages. Oh, sorry. And here as well, it would appear something like that. So these are outcrop patterns. Now you can imagine that I can draw a series of sections on these folds oriented differently, and we can get different kind of outcrop patterns. It can be a vertical section, it can be a horizontal section, it can be an inclined section, and so on. So the best possible way when you have a single fold is if you see through the perpendicular section of the fold axis. But if we have a superposed deformation, then it is not very easy to figure out that which fold axis I should take to have the profile section, number one. Number two, if the fold axis is curved, then how to get the successive profile planes and so on. But in the field there is no control, so they do appear in many different ways, and therefore the superpositions also appeared in the field in many different ways. And this is exactly what we are going to learn, that what would be the typical outcrop patterns of these four types of superposed deformation that we have just seen. Now in this image, these three are given here. In the previous slide we have seen different kinds of outcrop patterns of these three very simple folds. So what you can do, you can take these three images and you can make them sections in different ways and see what kind of outcrop patterns you get out of it. You can use also all other kinds of folds. It can be inclined, it can be tight, it can be open, and so on. Now let us have a look, how do we get the superposition pattern of type 0. As I have told in the very beginning that the superposition is redundant in type 0. So what we see here, that F1 and F2, these are parallel to each other in type 0 because it is just getting folded in a very similar way. So therefore S1 and S2 as well parallel to each other. So the outcrop pattern, so if you cut it along a horizontal plane, it would show up like this. If it is an inclined, it would show up like this. But this is somehow, this section is, as you can see, it cuts both F1 and F2. And if you cut this in a different angle, which is here, then it may show up as a folded structure. But this is something we really cannot interpret looking at it, whether it is type 0 superposition or it is a single type of fold. So this is how it is with the type 0 type of superposition. Now outcrop pattern of type 1 is very interesting, and it produces mostly what we call dome and basin structures, or in other ways oval or somewhat rhombic or lozenge shaped outcrop. Now the curved hinge line of an early fold, that is F1, must meet the plane of outcrop at least 2 times to produce dome and basin structures. We will see this how it happens. And the type 1 interference will not give, however, the characteristic dome and basin outcrop patterns in all outcrop faces. For example, if you see it along the F2 axial planes, then what you will get? You will get the sinusoidal pattern of F1 fold, and vice versa is also true. If you see it along the F1 axial plane, you will see the sinus pattern of the F2 folds. We will see it soon. So what we see here in this, so this is, as you can imagine here, that we discussed about it. This is how F1 is going like this. and this is how your F2 was moving. So this is your F2 and this is your F1. Now this section is your S2, the green one, and this is your S1. So this S2 is actually the section of here, this one, as you can see. So this is showing up a sinusoidal pattern on S2, you see this. And S1, if you see it this way, then you see also the sinusoidal pattern, and you may not figure out that this is a product of superposed deformation. However, if you cut it along this plane, then you see something very interesting, and which you are going to see in the next slide. So these are known as dome and basin structure. The type 1 interference produces dome and basin structures, as we talked about, so oval or somewhat rhombic or lozenge-shaped. So you can see here that these are your basins, so that means it is like a bowl, and these sections, as you can see here, these are like a domal structure. So these things, if we can talk about, they are dipping towards the center of this basin, and this layer, if I talk about, they are dipping away from the top of the fold. You can actually figure it out here. So they are dipping this side, and therefore it is producing a dome and basin structure. Do we see them in the field? Yes, we see them in the field. As you can see here, that you have this, you can figure out that these are your some sort of folds going on here, and here you have a closure where the fold axis is going something like that, and this here the fold axis is plunging towards this side, and here fold axis is plunging towards this side. So they are converging here, and the beds are dipping also towards the center. So this is a basin. On the other hand, if I consider this particular area, you see here the fold axis is plunging to this side, here the fold axis is plunging to this side, the beds or the form surface is in this side dipping here and in this side dipping here. So this is a dome and this is a basin. And this is how we produce alternatively dome and basin structures. There is another example. Here you can see this is again a very classical photograph from Professor John Ramsey. So you can see this is your one set of axial traces. Of course, you don't see it in 3 dimension, and another one is going like this. Here it's going like this. So this is the interaction between F1 and F2 producing the dome and basin structures in type 1 superposition. This is an experiment again performed by Professor Nibir Mandal, and you see here that these are your basins, these are curved here and here, and these are your domes, because when you cut the section the domes are out, and then you see them exposed in this way, and you see these are all dipping away from the hinge zone, which is somewhere here. The fold superposition you can study the best if you do some sort of experiments, and people have done it since long time, and this is just an example. Let us have a look what happens with type 2 superposition in terms of their outcrop patterns. The type 2 pattern of fold superposition is generally identified by crescent-shaped or mushroom-shaped outcrop patterns. Now you don't see them again in all sections. So for crescent or mushroom-shaped outcrop patterns, you can only see when F1 and F2 fold hinges meet more or less a planar outcrop face at least more than 1 point. So that means F1 has to pass through the plane at least 2 times, and same for the F2. Now also in other sections you can get a sinusoidal patterns when you see F2 hinge meets the F1 hinge at 1 point only, and you can also get a hook type pattern, and we will see how does it work. So again this is what we have drawn. This is your F1 going like this, your F2 is going like that, right, and this is your S1 and this is your S2. So clearly on the S2 surface, which is this one, you see the fold patterns of S1 only, and you cannot figure out whether this is a superposed deformation or not. However, you can see some excellent features when you make sections in different ways. So, this is typically a crescent shaped outcrop, where you can see the F1 is going like this and F2 is going like this, and this one is known as mushroom, as you can see from this typical shape. So, it is like this, isn't it? So, this is like a mushroom, and this is known as mushroom type of mushroom type of exposures, and again you see your F1 is going like that here and F2 is like this. Okay. The crescents are also here, as you can see here the F1 is like this and F2 is coming like that. This is a crescent, as you can see. So, F1 is something like that. This is your first fold axis and this is your F2. In this example, you can also see it is going like this. So, again this is your F1 and this is your F2. Here it is a tilted outcrop, but you still can figure out the shape of the crescent. This is your F1 and this is your F2. In this image, this image you can also see how this is folding here, and the same layer is coming up here like this. So, this is a very complex pattern, but if you understand the geometry of superposition, you can figure it out. In this image, which I received from Professor Biswal, you can clearly see that at the center we have a crescent, but we have an excellent mushroom on this side. So, the best is if you do a geometric analysis and you figure out. So, again you see this is your F1 and this is how it got this entire fold that you see here. This is because of the second deformation and the trace of the F2 going on along this side. This is an excellent mushroom as well. You can see here this is the outcrop pattern. So, clearly you can figure out this is your F1 here and this is your F2. So, this is how it works, but by the way this is not the first fold we see here. This is a highly deformed terrain. So, this could be a many second generation fold. So, we can define it as particularly for this. So, if this is n, then this is n plus 1. So, the n is the number of deformation we are looking at. Now, we can also see a sinusoidal pattern if we cut it flat. So, in this section you see the traces of this S0 here and on this surface, which is horizontal surface here. So, these are your S0, the form surface, and you see the traces of your S1 folds on this case, and you also see the S2 folds in this way. Now, you can also see the hook shaped pattern, something like that. It is coming like this, and this is known as hook because it is coming something like that. So, these hooks are also possible in type 2 superposition of folds. Now, let us talk about what happens with the type 3 superposition. Now, type 3 fold interference is essentially characterized by hook shaped outcrops. So, you also get them in type 2 deformation. So, you have to look in some other surfaces if you can also get hook shaped outcrops or not, or crescent or something like that, but they generally are very complex. So, you have to be very careful to identify that which type of superposition is actually what. Now, the hooks appear on the outcrop faces that intersect both F1 and F2 hinges. Now, sections again either parallel to F1 or parallel to F2 would not produce any typical intersection pattern, or it would be a redundant interference. So, what we see here again, as we have learnt in this previous slides, that this is your F1, this is your F2, this is your S1 and the green one is your S2. So, S1 is curved, that is why it is non-planar, but it is cylindrical because neither F1 nor F2 are curved. So, they are straight. Now, you can clearly see in this section we see this hook shape. Okay. So, section perpendicular to F1 and F2 would give you a hook shape, or if the outcrop pattern cuts at an angle F1 and F2, you would see essentially a hook shaped pattern like here. So, we cut at an angle. So, this was your F1 and this one is F2. So, this is the plane, this outcrop pattern that is cutting both F1 and F2 at an angle and producing this hook shaped outcrop. But if they are parallel to F1 and F2, then you can have outcrop patterns as you can see in this slide, and these are some sort of redundant superposition. Now, do we see them in the field? The answer is yes. First, have a look here. We see that this thin layer is folded something like that, the thick layer is straight, and then here we see a very faint hook formation. Okay. So, this is again your F1, this is your F2, they are aligned almost perpendicular to this projection plane, and these are your traces of the axial planes, and this is another one. So, you can figure out this must be your S1 and this must be your S2, but we can see them in a much detailed and better way. So, this is again one hook, as you can see this is one fold axis and this could be another fold axis, where this one is certainly F1 and these are F2 fold axis, they are parallel to each other, and in this section that we are looking at, they are approximately perpendicular to the plane of view. And here as well we see this must be your F1, and then these two fold axes are where it got maximum curved. This is the trace of S2, this is the trace of S1 in this case, and these are your F2. Okay. I conclude this lecture of fold superposition and also the conclusion of this week's lecture. So, I repeat, it was again a long week. I am sorry for that, that you have to spend time in front of your computers or something for quite a long time this week, but I believe this is something we should understand and learn as an undergraduate student of structural geology. And in the next lecture we will actually continue this superposition, but we will see them in a different way. Next week is assigned for Boudin's, but I would like to spill part of it to the next lecture, and we will look at things in micro scale and we see how these different kinds of planar fabrics appear in the field. So, what are their mutual relationships, what are the overprinting relationships together with the metamorphism, because during metamorphism we form some new minerals and the new minerals grow during deformation, and while they grow they include or they produce some characteristic microstructures, and these microstructures are very crucial and important to identify when and how the deformation had happened. So, stay tuned, I will see you in the next week. Thank you very much.